Good morning. So, this would be the second lecture on the topic of measurement of temperature. So, in the last lecture, we had seen a few types of temperature measurement devices, a few non electrical temperature measurement devices like the thermometers with liquid in glass thermometer, bimetallic, and pressure thermometer, which use a wood on tube. Okay, we have also seen one electrical method or the one electrical principle for temperature measurement, that is thermoresistive measurement, where the resistance of some material changes with temperature, like in an RTD, whether where there is a positive correlation with the change in resistance to the temperature, and a thermistor in which there is a negative correlation. And in today's lecture, we would look at the thermoelectric effect for to be used as a means of measuring temperature. That is, we look at the thermocouple, wherein by thermoelectric principle, what I mean is that whenever there is a metal in which there is a temperature gradient, a electric potential is also developed across those 2 points. Okay. We also look at radiation methods, which can be used as very high temperature, where the emitted radiation is analyzed from a really hot body and the temperature is estimated. So we look at pyrometers and bolometers, which are two such devices. So the first transducer that we will look into is the thermocouple. So thermocouple is basically a metal strip or wire, uh, or actually there are two metal strips which are connected at both ends, and the two ends are kept at different temperatures. Okay, so there is a metal strip which is kept at whose both ends are kept at different temperatures, and it uses a principle of a Seebeck effect or the thermoelectric effect, which says that when the ends of a metal strip are kept at different temperature, an EMF is generated along the length of this metal strip, and this EMF is a function of the difference in the temperature, or is a function of the temperature distribution along the thermocouple, or along the metal strip. Okay, so it depends upon how T1 varies to T2, and it also depends upon how this material is there in between. Okay, note that here we are talking about only a single metal strip. Okay, so let's get into a little mathematics of it. Okay, so this is what is happening. So the EMF across these two ends, across T1 and T2, is a function of is sigma of x comma t, where x is the distribution of the material along the length of the strip, and t is the temperature at any point in the strip. Okay, so E sigma x comma t is a function of both x and also the t, the temperature at both the ends. Okay, now what is needed is that it seems that it is easy to now uh, measure this EMF T1 and T2, but the point is that how are you going to measure this? Because you have to access both these ends, and so you have to have another connection here. Okay, so what you end up with is a setup where there is one metal strip here, there is another metal strip here. Okay, and to be able to measure, and both the ends of both these metal strips are kept at different temperatures. So if we have A as one material and B as one material, and if you use B as the means of connecting these two terminals of the metal strip A, Then we can take a voltage here, okay, and compute the voltage difference and get a thermocouple. Okay. Or we can also measure the current flowing through the circuit because of the potential difference. Okay. Notice here that the thermocouple is actually a point measurement device. Okay. So in here, this is the measuring point, and in contrary to the case of the thermometers, we just need to heat up this point, this one point, to the temperature T1 and keep T2 as some reference value to get an estimate of T1. So from E and from T2, what we want is to get T1. The other point to note is, let us have a look at this expression sigma x comma t and dt by dx. Okay. So there are two things. One is that the so sigma x comma t indicates the material distribution along the length, okay, and also indicates the temperature along the different various points. Okay. So let us say that the material distribution is constant. Okay. However, there is a change in temperature. So dt by dx is not equal to 0 is one scenario, and in another scenario dt by dx equal to 0. So what I want to point out is that this EMF is produced as long as sigma is also, anyway it's not equal to 0. So as long as sigma is constant, and when there is a temperature gradient, that is T1 not equal to T2, you would be able to get an EMF. On the other hand, if you have a situation where dt by dx is equal to 0, that is T1 equal to T2, it doesn't matter what is the material distribution, whether there is a variation in the material distribution along the length, the EMF would turn out to be 0. Okay. And now if we say that the temperature distribution the material distribution is constant, okay, then we can use the thermocouple as a measuring device in this manner. So if you assume that the two strips A and B are constant, then the integrand, the term in the integral, is going to be a function of the temperature alone for both the material A and the material B. Okay, so which would mean that the overall temperature difference that you have, okay, is the EMF that is produced in A minus the EMF that is produced in B. Okay, so sigma A of t minus sigma B of t, which anyway is just a function of the two temperatures T1 and T2. Okay, note that it is a function of T1 and T2, not necessarily T1 minus T2. We are not talking about the EMF being proportional or being dependent on the difference of the temperature. The EMF is a function of the temperature, of the actual temperature of the two ends. And if we look at the data tables, what we found is this relationship is almost constant. And if we try to plot E versus T, or express the expression E in terms of T, okay, when one of those terminals is kept at absolute 0, okay, so if we assume that T2 is kept at at 0 degrees centigrade, not absolute 0, at 0 degrees centigrade, and for different values of T1, if you see what is the EMF, you get an expression like this, and you can contrarily you can get what is T from E using this expression, and you can see that the higher order terms, the quadratic and higher order terms, are orders of magnitude less than the order of magnitude than the coefficient for the linear term. So this is almost linear. However, it should be kept in mind that this linearity is not absolute, because so as temperature increases, these higher order terms will also matter. However, for most practical purposes and in most relevant temperature ranges, the E versus T relationship can be taken to be linear. And for this particular relationship, this is taken from this source, ASTM Manual 12, table 10.20. What I would again like to reiterate is that here what we have said is T1 equal to T and T2 is 0 degree centigrade. Okay, so this is important, that to be able to determine the junction T1, which I say is hot junction temperature. Okay, what we need is to know the cold junction temperature. Okay, let's proceed further and let's look at a few thermocouple laws of how the EMF and temperature are related. So the first law is that the thermal EMF of a thermocouple with junction at T1 and T2 is totally unaffected by the temperature elsewhere in the two materials, assuming the two metals are homogeneous. So if you have T1 and T2, these two junctions at this particular temperature, it doesn't matter whether the temperature increases or decreases along the length. What is required is both the junctions are at the same temperature, then the net EMF is going to be the same. Okay. The second law is that even if you introduce a third material in between, okay, so you have T1 and T2 with the junctions as the junction temperatures between A and B, and you introduce a material, the third material C, as long as the two junctions formed between AC and B, AC is in both cases, AC in both of these cases, as long as both the junctions are at the same temperature, the net EMF doesn't change. So this can be taken as that you can say that the net EMF is, say, sigma of A, or rather we can say that net EMF in this case is in the first case is sigma A of T1 T2 minus sigma B of T1 T2. Okay, in the second case it is sigma A of T1 T3 minus or plus sigma C of T3 T3 plus sigma A of T3 T2 minus sigma B of T1 T2. Okay, and this sigma C T1 T3 T2 is not going to affect at all. Okay, and this thing sigma A of T1 T3 plus sigma A of T3 T2 would be equal to sigma A of T1 T2. So basically what I want to re-emphasize is that this junction, this addition of another material whose both junction are at the same temperature has no effect. And here too there can be temperature variation along the third material C, where you have temperature T4 and T4 and T5 at different points. However, both these junctions, new junctions, are at T3, so that will cause no effect. Okay. The next one is that instead of C3 being at A as a part of A is taken from A, even if the third material was replacing the junction, and both these two new junctions are at the same temperature, then too the net EMF is going to be the same. Okay, so that's the third law. The fourth one is the one that I had actually used, that if you have, so it basically says that sigma A of T1 T2 is the same of sigma A of T1 sorry, I mistook this. So there's a different law. So let me explain that properly. Okay, so the fourth law is that if you have different materials, so you have C here, okay, so this is between A and C, this is between C and B, okay. So if you add these two EMFs, what the resultant is the same as the thermocouple between with the two junctions being formed between the material A and material B. Okay, and actually this is actually quite simple to understand, as long as if the two materials are homogeneous. So this will be some sigma A T1 T2 minus sigma C of T1 T2 plus sigma C of T1 T2 minus sigma B of T1 T2. So this will turn out to be the same expression. This will be sigma A of T1 T2 minus sigma B of T1 T2. Okay, so that was yeah. Moving over, now if a thermocouple produces an EMF even when the junctions are at T1 and T2 and E2 when the junctions are at T2 and T3, then it will produce E1 plus E2 when the junctions are kept at T1 and T3. So this is the principle that I had used earlier, okay, where the temperature, even if the temperature changes, it's not going to affect the junction. The material changes also, it doesn't affect junction. Okay, so however, it should be noted that here what we are talking about is the set of two temperatures. Okay, that is, if you have T1 and T2 here and T2 and T3 here, then the EMFs are additive. Okay, but if you have T1 and T2 here and you have some Tx and Tx, or let's say if you have Tx on one side, you have T1 and T2 here, okay, and here you have T2 and T2 minus T1 minus T2. So the difference here is the same as difference here. Okay, this does not mean that this will be even. So here if it is even, this does not mean this is even. Okay, so the EMF produced here is not a function of the difference in the temperature. It is basically a function of these two temperatures, and if one of the temperature is kept at a standard, it basically turns out to be a function of the hot junction temperature. I am reiterating the same point again and again, okay, because it may be a common misconception by seeing the almost linear characteristics of the thermocouple. A false analogy can be taken, saying that the EMF is a function of the difference in the temperature, but that is not the case. Okay, now let's look at a few thermocouples to see what we are dealing with. So this is a set of thermocouple, the characteristics of thermocouple denoting the induced EMF in the thermocouple in millivolt. Okay, assuming that the reference junction is at 0 degree centigrade or 32 degree Fahrenheit. Okay, and various types of thermocouples, various junctions are used. Either you have chromal constantine here, you have iron constantine here, your copper constantine here. Okay, you have platinum rhodium versus platinum here. Okay, and and various thermocouple depending upon the temperature range that is being measured, different thermocouples need to be used. Okay, and even though technically most of the a lot of metals are theoretically forming thermocouples, only a few combinations of them have enough linearity in their characteristics to be actually used as thermocouples, and some of those examples have been kept here. Okay, and even in this, depending upon factors like cost or temperature range being measured, you have to see which is the appropriate choice of a thermocouple. Okay. So, for example, if you look at the platinum rhodium thermocouple, okay, you see that this one has a low sensitivity. Okay, however, it has a very wide temperature range. Okay, from 0 to 3000 degree Fahrenheit or 0 to 1500 degrees centigrade, and moreover it is a very accurate thermocouple with an error in this range. The error is 0.25% or less. Okay, on the other hand, if you look at the copper constantine thermocouple, okay, its sensitivity is almost 10 times the sensitivity of the platinum rhodium platinum thermocouple. Okay, however, the it's not so accurate. Okay, error can be up to 0.5 to 0.75%, and moreover its range is also quite displaced. It can only measure up to plus 350 degrees centigrade, and basically half of its range is in below freezing temperatures. Okay, so depending upon whether you want to accurately measure lower temperatures or have a measurement of higher temperatures, okay, you have to make a choice of which thermocouple is to be used. Yeah, so if you want to measure a larger range, okay, then you want to go for this thermocouple, platinum thermocouple. And if you want to measure a smaller range below freezing and with higher sensitivity, you may go for the what you call copper constantine thermocouple. Okay, let's see that some of those unintentional effects that can affect in a thermocouple. So now in this thermocouple, we have to measure the EMF across these two junctions. Okay, now these two junctions are made. So this junction is at a reference temperature. Okay, and this junction is at the temperature that is to be measured. Okay, we have to take another junction here. Okay, make two junctions here, and probably you are going to use copper contacts here, and let us say this goes into an amplifier, because we have seen that the thermocouple output is in millivolts, and then it has to be made into a larger, maybe bought into the range of a few volts for it to be really used. Okay, so there is some silicon here. Okay, there is some copper to silicon contact here. Now what is happening here is that what we had originally assumed that there are only two junctions, okay, where dissimilar metals are being joined and which are kept at some temperature. Okay, now we see that there are more junctions being formed here. Okay, so let's see that. You see that there are two junctions here, and there are two more junctions here. Okay, and what is the effect of this? Now, if these junctions temperatures are not coordinated properly, probably there can be some error. Okay, let's see how that may affect. Okay, so this is a rough diagram of what is being done here. Okay, you have T3 here. Okay, so you have T1 is the ion constantine thing. Okay, and T3 is the junction between iron and copper and constantine and copper. Okay, of course this is a bit different from this case. Okay, so here this is a reference junction. So here you have a reference junction here, and there are unintentional thermal junctions being formed at different locations. This circuit that I'm going to explain is a slightly different one, where you have a thermocouple between iron and constantine. Okay, you have a reference junction here, and you have a hot junction here, and you have a reference junction T2 that is here. Okay, we would have wanted to join this too, but then after joining we may not be able to, then there is no proper access to the any information about the hot junction. So what we are doing is that both this ion and this constantine junctions are joined by a copper wire. Okay, and these two are kept at the same temperature. Okay, now again, since a amplifier is needed, this has to be again connected to a silicon substrate again. Okay, or the silicon circuitry, and that junction is kept at T3 between copper and silicon. Okay, that is being displayed here. Now let's see that what is happening in this case. Okay, now let us start from the silicon part. Okay, let us assume that both the parts of the silicon are kept at the same temperature. Okay, now along this copper, let me use a different color so that it is easier to see. Okay, so along this line between copper and constantine, okay, and since these two junctions, this is at T3, this is at T2, and we can assume that T2 is greater than T3, there is an increase in the EMF. Okay, and again once it goes along the constantine also, there is an increase in EMF at a higher rate. Okay, and around the ion, since there is a decrease in temperature, there is a decrease in EMF. Okay, and here along copper, again there is a decrease in EMF, and since both of these junctions are at the same temperature, this is constant. Okay, what we wanted to measure was the difference between these two junctions. Okay, that is, we wanted to measure this EMF. Okay, the junction here minus the junction here. Okay, what you are actually measuring is this EMF. Okay, and if we are sure that these two differences of these two junctions. So this is at T3, okay, this is at T2, this is at T2, this is at T3, okay. Now we are assuming that both these junctions are the iron and copper and constantine and copper junction, okay, if they are kept at T2 at the same temperature, then the problem seems to be solved, okay, even though there is unintentional junctions being formed. However, let's see a more general scenario where these two junctions are not at the same temperature. Okay, if these two junctions are not at the same temperature, this rise in here is not equal to this fall. Okay, which would mean that this measurement and this measurement is not equal. So to be able to reliably use the thermocouples, while there is a necessity, while there is a practical necessity that we may have to add up new junctions into the circuitry, okay, it is always advisable to keep the entire measurement circuitry at the same temperature, okay, because we may not know that whether these two are kept at the same temperature, okay. Further, we may also not know what this temperature, even if they are kept together, we may not know what the actual temperature is. So it is better to keep T2 equal to T3 so that this entire thing, the copper is also flat here and the copper is flat here too. So we are actually measuring the same EMF, okay. Or an alternate to that, which may sound quite simple, may sound simpler, however it may be really costly, is to do this. So instead of having copper here, use iron, and here instead of copper you use constantine. Okay, now what would happen is that there are fewer junctions, there is no thermal junction here. So this is one end of the thermocouple, this is another end of the thermocouple, and this is the third material whose both ends are at the same temperature. So we have T3, which is the reference instead of T2, and we have T1 as a hot junction, and the temperature can be measured. Now we know that in case of thermocouple, each thermocouple is going to produce a EMF of only a few millivolts, okay. However, this EMF can be added up by connecting the thermocouples in series and making something called as a thermopile. So all these hot junctions are at the same temperature, all these cold junctions are at the same temperature, and the metal strips are connected alternately. So here you have a 3-junction thermopile or 3 thermocouple junction, okay. So which would mean that the output here would be 3 times the output of one thermocouple, okay. And basically this would mean that the sensitivity is going to be increased, okay. And in most applications, wherever you are using a thermocouple, basically you would be using a thermopile only, because it's quite easy to stack the thermopiles together and increase the sensitivity by combining them into a thermopile, okay. This is a typical structure in which a thermopile would look. Alternately, note that the thermocouple as I said, that is a point measurement device, and which means that it is only specifically talking about what is the temperature of the bead that is formed at the junction, at the hot junction. However, it may be necessary that I have a large object and I want to measure the temperature of that object, which would mean that I have to take an average of temperatures from multiple points, because a larger object may have its own temperature distribution. Okay, so to get an average temperature too, you can have a thermocouples. Okay, so here what you have is that these are different temperature at different points of the body, of the hot body, and the cold junction is kept at the same temperature, and all these thermocouples are joined together. Okay, now if we assume, or if we take into account, if we assume that all these three thermocouples, all these junctions, all these metal strips have the same resistance, then the effective EMF that is produced across this parallel combination is going to be an indicative of the average temperature, because the EMF would be the average EMF of this E1, E2 and E3. Okay, that is because if the temperature is going to be if the resistance is going to be R, okay, then the resistance of the entire parallel combination is going to be R by N, and in each of these three parts, see, EI by R is going to be the current. So this would give an EMF that is EI by N, summation EI by N. Okay, and this effective EMF is going to be indicative of the average temperature. Now let's move further in and look into the advantage and disadvantage of the thermocouple. Okay. Thermocouples are cheaper than RTD and they are quite well suited for point measurements, and their range of measurement is much larger than what is feasible in a typical RTD. And the response, since the junction needs to be heated up, okay, and the thermal capacity of the entire thermocouple is not of concern. Okay, so since the junction can be heated up very quickly, particularly in the case when the hot junction is already at a large high temperature, the thermocouple's response time is really quick, in less than a second. Okay. However, the accuracy that is afforded by a thermocouple is lower than the accuracy that is possible in an RTD or a thermistor. Okay, because you see that in a thermistor the per sensitivity is, though sensitivity is low, the accuracy is quite high. Okay, and a larger accuracy can even be achieved by using a Wheatstone sort of a bridge. Okay, and because the hot junction is dependent on the two materials, the entire reading is dependent upon what are the two materials being used. Any contamination of the material is going to seriously affect the reading. So this junctions need to be shielded properly to avoid any contamination. Okay. Further, what the entire in case of a contamination, let us say there is a thermocouple like this. Okay, so in case of a contamination, even if T1 and T2 are kept at the intended temperatures, if there is a contamination that is happening, let us say in this, which sort of changes the material property, material density somewhere along the middle, okay, that is going to cause an unintended two junctions to be created. Okay, and there is no guarantee both the junctions are at the same temperature now. So this is again going to cause a spurious reading. So the what do you call the purity or the consistency of these junctions and maintaining that is very important in case of thermocouple. So shielding of the entire thermocouple is also a very important thing, or else you would need to have connecting wires of the matching material, which would also will also lead to further complicated circuit. That was as far as thermocouple is concerned. Let's go into radiation pyrometry. Okay, so radiation pyrometry, as the name implies, it uses the electromagnetic radiation emitted by any body that is above absolute zero. Okay, so if you have a hot body with a temperature Th and a cold body at a temperature Tc, there is always some electromagnetic radiation that is flowing from the that is going from the hot body to the cold body, and it is absorbed by this cold body, and the amount and the emission rate from here to here is going to be is given by this expression, which depends upon the difference of the temperature, or the depend upon the temperature of hot and cold body, not the difference. It is the fourth power of their absolute temperatures. Okay, where EH is the hot body's emissivity coefficient, and sigma is the Boltzmann constant. Okay, and these sort of parameters are generally used for measurement of high temperatures, or temperatures greater than 500 degree centigrade, above the range at which thermocouples can be generally used. Okay, and since they are basically dependent on the amount of radiation that is incident, and the radiation itself is dependent on the is a function of the temperature of the hot and cold body. Okay, these are better suited when this difference is large enough, and hence the temperature range or the feasibility range is greater than 500 degrees. In addition, they are generally used in for temperature where the emission is mostly in the visible or the IR region of the electromagnetic spectrum. And the other main advantage, or the main advantage of radiation parametry is it's a non-contact type instrument. Non-contact type instrument, which means that I can have a pyrometer, and the pyrometer need not be in the it need not be located in the location where the hot body is. So I can have a hot body that is emitting radiation, and I can have a pyrometer here which is at some cold temperature, and by measuring the incident radiation, the hot junctions or a hot body's temperature can be inferred. What is to be remembered here is that the concept of the pyrometry is dependent upon the emission spectrum of the hot body, and therefore the temperature and that is a very important factor. Okay, we should know what is the emission spectrum of the hot body to be able to predict what is the temperature of the hot body. That is one of the one of the disadvantage of using a radiation method of radiation pyrometry, because you need to know what is this epsilon h. Okay, and there are one or two different methods by which radiation pyrometry can be used, and the exact method will depend upon the target temperature range. Now, I have been saying that about the emission spectrum of a hot body. So this is usually a typical power spectral density of a hot body. and that is the radiation is, first of all, the radiation is not concentrated at any particular frequency, and it is spread over a frequency range or a wavelength range, and it peaks at a particular wavelength, which is a function of the temperature. Okay. And what can be observed is that as the temperature increases, the most of the radiation, okay, falls in the wavelength range or the frequency range, okay, where more than 90% of the radiation energy is concentrated. It shifts. So lambda decreases, okay, as temperature increases, okay, and similarly the peak power also increases as temperature increases. You can say lambda decreases or the frequency increases as temperature increases. So in radiation pyrometry, what we are looking at is that we are measuring where this peak amount of radiation is happening, okay, and from that inferring what is the temperature. Okay. Now, if this peak is happening in the visible range and more so near the red part of the visible spectrum, we will use optical pyrometers. Okay. And in this setup, what you have is you have a filament whose color is being compared with the hot body background. Okay. Let me explain that. So you have a incoming radiation coming into this setup, okay, and you have an eyepiece from which an observer is able to see and compare, and there is a bulb here whose and the bulb's filament temperature is being adjusted by a adjustable rheostat. As the rheostat position changes, the current changes, and as the current changes due to the I square R behavior, the temperature of the bulb increases or the filament of the bulb increases, and hence it will glow from infrared to the visible range also to red. So what we are doing is that when we compare the color of the radiation that is coming here and the color of the filament, okay, when the color merges, then we take this as an indicative of the temperature, which means that the temperature of the filament here is the same as the temperature of the incoming radiation, okay, or it is dependent on the it's has a one-to-one relationship between this temperature and this radiation's temperature. Okay. In this case, you have filament being cooler. Okay. Here you have filament being hotter. Okay. When the filament just disappears in the background, we can say that the temperature can be measured. And now, since the filament temperature is a function of the resistance and hence the current reading can be indicative of what is the temperature. By putting an appropriate filter here, we can basically shift the say the frequency spectrum to a lower range, okay, lower frequency range or higher omega, higher wavelength range. So which would mean that with a filter, instead of having a 1400 degree centigrade temperature, a 3000 degree centigrade object whose typical spectrum would have been towards the blue, okay, with a filter it can be shifted a bit towards the left and appear more redder and then being compared. Okay, so by using filters you can increase the temperature range also, and without filter the usual temperature range is from 1600 to 600 to 1400 degrees centigrade. Moving further, the disadvantage of the optical pyrometer, or any the limitation of the optical pyrometer, is that its calibration is dependent upon the emissivity. Because emissivity is dependent on the material, the calibration of the radiation parameter of the optical parameter is dependent upon the what is the target material. So you need to know the target material, and since there is a human involved, small variation in the error, small human induced errors of say plus to minus 10 degrees centigrade can come, because you can't differentiate between the colors to such an accuracy from a naked eye. Okay. In addition to that, the emission spectrum is also not so precise that you will have the peak at one particular frequency. You may have a peak that is not so sharp, okay, which would mean that there is an inherent error of say plus or minus 5 degrees in the reading on top of the human induced error. And the third factor is that since you have a human in the loop, the environment in which the optical parameter can be used is also restricted. It cannot be used in the environments where there are fumes which are harmful to the naked eye or to the human eye. Okay, and maybe if it's a toxic environment, optical parameter may not be useful. So a simple solution for that is to remove the human element out of this, and here is where the usual radiation parameter comes into picture, where instead of the eyepiece in a that is used in an optical parameter, you have an energy detector. Okay. And the energy detector captures all the radiation and translates it to some quantity that can be measured electrically. So it can be a photo detector that basically measures the light that is coming in. Okay, it can be an RTD, okay, which changes resistance depending upon the incident radiation's temperature, okay, and or it can be a thermopile also, where a thermocouple is being used. Okay, here in this figure, what you have is a vacuum thermocouple. So there is radiation coming in that heats up the thermocouple's hot junction, and there is a appropriate reading that is being measured. Note that the temperature to which this hot junction is uh, heated up is not the same as the temperature of the hot body. Okay, this hot junction's temperature is indicative of the amount of radiation that is falling. It is not really equal to the hot body's temperature. And since the radiation that is falling is indicative of the amount of the hot body's temperature, TH is indirectly determined by the hot body temperature. Okay, they are not equal, but they have a one-to-one relationship. Similar to RTD, where the resistance changes with temperature, you also have a bolometer, which is a device which consists of a material whose resistance changes in response to incident of intensity of incident energy. Okay, so the temperature of this bolometer is not changing, but its resistance changes depending upon the incident radiation. Okay, and the incident, since the incident radiation energy is again indicative of the temperature of that hot body, then the bolometer can be directly used to measure temperature by connecting it as one of the arms of the Wheatstone's bridge, or using a dummy bolometer at the other arm for ambient temperature compensation also. The advantage of a bolometer is they are microscopic in size. So you see that there are a few micrometers in size, and because of this, they can be made into arrays. Okay? They can be fixed into arrays, and each of these bolometers, its temperature will be indicative of the amount of radiation that is falling on this particular region, and hence they can be used as some pixels of say objects like thermal cameras, okay, or even in space telescopes also, okay, where basically you are measuring the EM radiation only. So with that we come to the end of this lecture. Again, these are the same chapters that I had mentioned in the last lecture for measurement of temperatures. Okay. Thank you for your patience.